All right. So we're going to continue our topic today on solving trig equations. Before we get too far into that, I want to get out of your notes or whatever, and let's look at these right here as just kind of a reminder, because I have some practice I want us to do today. I want to start with this. So what I have here are, you want to see if you can match up the expression from column 1 into column 2. All right, so 38 through 42 matches with A, B, C, D, E. One of them. All right, so it's just a matching. Take a second to get your brain focused back on identities. Maybe you want to get out that list of identities that we have been working on. That would be fine for you to be able to refer to. Sometimes it's easier to see them. Trying to see which two match, one from column 1 and one from column 2. When you think you've got that right, check with your neighbor. Okay.
Yeah, just change it. Oh.
All right, that's good. That was correct.
Yeah. Multiply by 6.
Far so good. Just a second. Mom.
Wait,
Okay.
I'm talking about it. It's gotta be secant x. What do you say?
Try again.
So,
If you were to split one.
Go back to school then.
yeah, that's what I'm saying. That's some squares.
Which is tangent. On the right.
Alright, and then 40 is tangent. Or 40 is, yeah, 40 is, it's like, it's 1 over cosine, and then 1 over
He's not right.
sine,
I know that.
and then you multiply.
Tell me what you got.
1 times cosine and 1 times.
What is the identity? 1 over.
So,
Yeah, with these next. These aren't going to be quite as straightforward. Now, is there something else?
turn it into this.
This might be a two-step thing, not a one-step thing. Think 2 steps. Might take 2 steps to get from one to the other.
Oh, yeah, that's easy. Yeah.
Less in our head. Okay. So the middle, 30 minutes. So the other two are correct. The other two are- I agree. What, so tan squared, how does tan squared relate to?
They'll all be their own bit.
No, the screenshot that I took was on the,
Let's go.
we're only covering these, right? The typical quotient, Pythagorean, cofunction, negative angle. Even in
Sine
algebra.
here turns into 1 minus sine.
So the A can also be
Oh, yeah,
the
that's right.
tan squared.
So it's cosine squared.
What on the right hand
The only
side
thing
can
that
also
can
be
be
the
cosine squared is 1 over secant squared. So
No, it's gotta have a square, right? So if sine squared over cosine squared could be tan squared. Anytime we see a squared, let's go with some
So
sort of,
one. Right. Minus.
anytime you see a squared term and a 1, you're gonna think, what? Anytime I think this, I think Pythagorean, this, I think Pythagorean, right? How does that help?
Oh.
Yeah.
32 is E.
That's what I'm saying.
I just never thought about it.
Okay. It's a little tricky. It might take 2 steps, like I said, to get there. On some of them. You are correct.
How do you what? So C is C squared.
No. It's conversion.
Okay.
Use. Also use the strength secant and the
Because
Gotcha.
Well, I think we're nine.
yeah, what is sine squared over cosine?
How'd you get it?
We're doing this term.
Tell me.
Tangent squared,
Why
right?
are you using this?
How does tangent squared relate to?
We said secant two is.
No, but then-
Yeah.
Yeah. In the end, you're just like, whenever you're.
All right, let's think about this first one, right? So, or letter A, I should say. So if sine squared over cosine squared is equal to tan squared, correct? All right, we all agree that this could be tan squared, right? Okay, now if I come over to the column 1, notice that secant squared minus 1, secant squared minus 1 is equivalent to tan squared x, isn't it?
on there.
No, it's not. What is on there?
1 plus cotangent.
Oh, so secant squared x would be 1 plus,
Cotangent.
no. Isn't that what it said?
No, it says 1 plus cotangent u equals cosecant squared u.
Yes, you're right. Now go to the other one, the one for tan and secant.
1 plus tangent squared x equals secant.
All right, so if I have 1 plus tan squared is equal to secant squared, I can rearrange it to be secant squared minus 1 is equal to tan squared, right?
Oh.
Okay, we're rearranging them. They're like a puzzle, okay? You all may hate puzzles by the end of this, which is totally understandable, but that's what it is. All right, so 39 is A. That's what we're looking at, right? Can I rewrite? And it's sometimes going to take 2 steps. Not always, mostly maybe.
So then we gotta turn it into cosine.
So maybe you need, yeah, just keep working on it.
Okay, so you can rearrange these things, so 1 plus sine squared.
Long questions.
You got about 2 or 3 more minutes to finish this up.
No, that 41 is staggered in 1. 1 plus sine squared.
Obviously, how the other 2 go, and figure out why. Good. Yeah. Process of elimination. Yes. That's correct.
I think he has some. So 39 goes with 30. You already did this too, so 40 goes with.
Well, give me letters.
Oh,
38 C.
Yeah.
39 A.
Yeah.
40 E.
Yep.
41 E.
What?
B. 42 is.
Obviously.
The only thing is, I saw everything with the lessons, right? Understand?
40.
It's just,
Yeah.
I'm trying to remember how to like. One, I get to one.
What is this?
Oh, is that a, yeah.
That one's. No.
One minus sine squared.
Okay,
Cosine
we got pretty much. We gotta move on, but let's put some answers up here, okay? For 38, we have C, correct? And that's because we can rewrite this as negative sine x. So notice that tan times cosine looks really close to that configuration for the quotient identity, right? We're just missing that negative sign. That's kind of throwing us off, and that came in because I can rewrite this as negative sine x, okay? 40 would be E, Okay,
How, so see, what a minute. I don't know.
so if I have secant x over 1 over cosecant x. Secant is the same thing as 1 over cosine. 1 over cosecant is the same thing as sine, which is sine over cosine or tangent.
Oh,
Okay? Okay, so we got A, C, E. Let's go with 42. 42 was what, everybody? B, yeah? Okay, so by process of elimination, that's going to give you D, correct? Okay, so D is this one right here, but I want you to think, what is cosecant squared minus cotangent squared?
One.
It's 1. So that can be 1 plus sine squared. Okay? Okay,
Oh, yeah,
so,
that was much easier.
yeah.
Okay. So,
All right, so practicing with those puzzles, right? Brain teasers. You all like brain teasers.
I'm not gonna like it anymore.
Make my head.
Okay. All right, so we'll come back and we'll practice some more identities. Right now, what I want to get our lesson covered in is solving our trig equations. Now, for the most part, remember that we said that if we think about the graph of any of our, let's say the graph of sine, just talk with the graph of sine, right? The graph of sine goes on forever, doesn't it? Right? The domain for that would be all real numbers, correct? All values for x, negative angle measurements as well as positive angle measurements, because it just keeps bouncing back and forth between 1 and -1. So when we think about solving equations for our trig functions, we have multiple angles that could be a solution, right? So most of the time, if I ask you to solve an equation, I am going to restrict the domain. I don't want to know all the angles. I'm going to only be interested in the ones in theory between 0 and 2 pi. Remember, bracket means inclusion. Parentheses mean up to but not including, because 0 and 2 pi repeat, don't they? That measurement does. So when we're looking at these, we are going to be finding the solutions for these equations on the interval between 0 and 2 pi, which means what mode would I normally be in? Radians or degrees? Radians, okay? So that's that interval right there is telling me what mode I'm talking about, like radians versus degrees, and it's also telling me what my solution set looks like. If I ask you to find all the solutions, then I'm going to show you what that looks like, okay? So just to kind of set that up for us. Now, when we solve our equations, most of the solutions that the process for us solving these goes back to the algebra that you've already done. Most teachers, most math teachers will tell you that students fail at at calculus, not because of what they learn in calculus, but because of their algebra skills, okay? So this is really just algebra. So don't be afraid of solving these because you know how to solve an equation. I have all the confidence in the world that you all can solve an equation. So what we're going to look at here says, the first example is 5 sine x is equal to 3 sine x plus the square root of 3. And that's our equation we're looking for. Ultimately, I'm going to end up finding all the solutions for this. What I want you to notice here is how many terms, let's just get some vocabulary out here. How many terms do I have here? I've got 3 terms because it doesn't matter on both sides, we're going to count it up. So I have a 5 sine x, a 3 sine x, and a square root of 3. If I have something separated by a plus or minus or an equal sign, that would be considered a term. I got 3 terms here. 2 of those terms are the same trig function, right? They're both sines. And then the other one is just a number, all right? And so when I think about solving this, let's say I had 5x equals 3x plus the square root of 3. What would I do? I would collect my like terms on the same side by subtracting, right? Same process here. So we are going to subtract 3 sine x from both sides to get 2 sine x is now equal to the square root of 3. Now the variable that I'm interested in is coming here in that trig word, right, in the sine function. And so what is that? What do I call that number in front of that? What is that called?
Coefficient?
It's a coefficient. So if I want to separate the coefficient from the variable, what process did I use? Division. I'm going to divide both sides by 2. Sine x is now equal to the square root of 3 over 2. Now, we don't normally write this. I don't normally write this, but, and so you don't have to write it right now. I'm just going to show you what we normally do. In order for me to get that variable, now the variable we are talking about, x, is hiding in that argument or angle position, right? It's kind of inside the function. And so what we do in order to get it out of there would be to take the inverse of both sides, the inverse sign, because we spent time last week talking about a function composed with itself gives me back the argument. This is the reasoning behind our process here. Now, what we're asking then is, what angles, when I take the sine of it, do I get positive square root of 3 over 2? So before you answer me, I know that sine is positive in which 2 quadrants?
1 and 4?
Quadrants 1 and 2,
1 and 2.
right? Quadrant
Oh,
1 and
sorry,
2 for
sorry.
sine. All right, now that means that I'm gonna get 2 solutions here, right? All right, so what angle, when I take the sine of it, do I get the square root of 3 over 2? Pi over 3 and 2 pi over 3. Right, those are the 2 angles that are the solutions for this function if I only wanted to restrict it and look at angles between 0 and 2 pi, correct? All right, well, I want to know all the solutions. And so we know that if I keep going around the circle again, I'm going to land back at pi over 3 again in the first quadrant, aren't I? So those angles are coterminal. Therefore, they are separated by how much? In radians? 2 pi. What if I go around again and I stop in that same spot? Okay, what if I go around again? I stop around the same spot. All right, so in order to say in general, all the solutions basically for the first quadrant, we would say pi over 3 plus 2 pi n. N being the number of times I'm going around the circle. 1 time around would be 2 pi, 2 times around would be 4 pi, 3 times around and so forth. All right, and the same process, the same concept is here with 2 pi n for the 2 pi over 3. Okay, so just to be clear, these answers right here are on the interval between 0 and 2 pi. And these answers here that I highlighted are all solutions. Most often I'm going to be asking you to just give me the solutions from 0 to 2 pi. Now, if I started out and I gave you the original equation up there, right, 5 sine x, blah, 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 and I said, I wanted you to check and tell me whether or not these 2 values here, right? So all you're given is an equation and 2 values. I want to know if they're solutions. How would you determine whether or not those values in fact are solutions? Plug them into the function and what should I see? that it works? How do I know it works?
When you have to use your calculator and plug it in on one side and do it again on the other and see if the two numbers match up.
This is what I was looking for. You don't have to use your calculator, but you are trying to check and make sure that the left-hand side does indeed equal the right-hand side. Very good. Algebraically, that's how we can check it. How would I check solutions graphically?
Can you just graph it and then find it?
Graph what?
Graph that function and then find it.
Hold on, Javi. Yes, we're gonna graph one side and then we're gonna graph the other, right? So if I come here and I go to Desmos or your graphing calculator, whichever one you want, and I type in y equals the left-hand side, which was 5 sine x, and I can call it y again, is equal to, excuse me, it's 5 sine x. Yeah. And then the other side was 3 sine x plus the square root of 3. And what am I looking for in that case? I got 2 scribbles up there. What am I looking for? How do I know that what the solutions are for these things?
Let's see where they meet the.
Where they intersect. When 2 graphs intersect, they are a solution. So that one point, right, that ordered pair, that x value and the y value is the solution for those 2 functions, all right? It's the one place where you plug in an x and you get the same y, okay? And so you can see here that we got pi over 3. You can see here we've got 2 pi over 3. And then if we keep adding pi, 2 pi, we're going to keep finding that iteration of those solutions. All right, so this is how you can kind of check and see what's going on. You can do this on your graphing calculator and find the intersection of 2 functions. All right. Trace, I think it's trace 5 or calc 5. Enter, something like that, right? Something like that. And you'll find the same values. They're a little bit harder to see on your calculator because your calculator is not going to give you back a pretty little radian value like Desmos can if it's in the right function form. But you still could figure it out. Okay. So now, yes, sir?
So do you have to do the plus 2 pi into, as part of your answer?
So you have to read the directions and you're going to give the answer based on what the directions are telling you. In this, I have asked you specifically in this problem to find all the solutions, which means plus 2 pi n for sine.
Okay,
Right?
so if the interval was different, you just change that 2 pi into that respective interval?
So let's look at this next example. And if you notice at the beginning, I'm going to restrict it to where I only want to know what the solutions are for one time around, right? So for one period, which would be between 0 and 2 pi.
Yes, ma'am.
Okay. So let's look at this one here. 2 sine squared x plus 3 sine x plus 1.
Quadratic equation, isn't it?
It is a quadratic equation, so it's a trinomial, right? 3 terms here, set equal to 0. And so how do we solve those? We do what?
Quadratic formula?
Let's not. That's second choice. It always works. Quadratic formula always works, but let's not use it this time. There'll be time for it. First choice would be factoring. Okay, first choice should be factoring. So when I factor this, leading coefficient is prime. The last number is prime. This should be fairly easy. Since it's already set equal to 0, we can jump straight in and factor. So I would have 2 sine x and a sine x. I've got a minus and a minus and 1. The only factors of 1 are 1. So let's just make sure we did that right. So I have a -1 times 2, which is a -2, plus a -1 gives me a total of -3 sine x's. So I have this factored correctly. This is what we call the 0 product rule, all right? I cannot solve an equation, okay? I can't solve an equation using factoring if it's not already set equal to 0. Okay, and it's a rule that says, okay, well, if it's set equal to 0, then I can take each of my factors, which are the things that are in parentheses. I can set each of those factors equal to 0 and solve. So I end up with two simple equations. I would have 2 sine x minus 1 equals 0. Sine x minus 1 is equal to 0. Starting with the left equation over here, I would add 1 to the right-hand side, and I would get 2 sine x is equal to 1. Divide both sides by 2, and I get sine x is equal to 1/2. So some angle, when I take the sine of it, gives me a positive value. We said that that is occurring in quadrants 1 and 2 for sine. What angle, when I take the sine of it, do I get 1/2? I get pi over 6 for the first quadrant, and what? 5 pi over 6 for the second quadrant. So there's two of my solutions. Let's move on to the second equation here, and I would get sine x is equal to 1. That's a quadrantal angle right there. Remember the quadrantals, I would have 1, 0, 0, 1. So x has to be what? Pi over 2. So I have 3 answers in my solution set. Pi over 6, 5 pi over 6, and 5 pi, and pi over 2 are all 3 of the solutions that occur on one period, right? Between 0 and 2 pi, which is all I'm asking for. I just want these that are occurring in that interval. Okay. So far we've looked at collecting like terms as a way to solve an equation. We've talked about factoring, all right, when you are using the zero product rule here. How about this one right here, 4 cosine squared x minus 3?
Wouldn't that be another binomial that you could factor?
That's a good question. Is it a binomial? And when I am going to factor that type of binomial, it's special because it's called the difference of 2 squares. So although I have 2 terms meaning the binomial, although they're separated by a minus sign, what I'm interested in is the first and the last terms have to be perfect squares. The first term's a perfect square, but the last term is not a perfect square, is it? Okay, so I can't just separate this out into the plus and minus, okay? So the other route to this is to use the square root property. In other words, let's get the squared term by itself. I do that by adding 3 to the right-hand side. Then what would I do? Divide by 4, because I'm trying to get the squared term by itself. And then what? Take the square root of both sides. So the cosine of x would be the square root of 3 in the top, divided by, what's the square root of 4? 2. And is this a plus? This is plus and minus, by the way. That's important. When I take the square root of a number, I get both the positive values and the negative values, right? That means then that I'm looking at what?
So does that mean you're gonna have all 4?
That's exactly right. I'm going to have all the positive values which occur in 1 and 4 for cosine, and I have all the negative values which occur in 2 and 3, right? Okay. So the cosine for square root of the cosine of what angle gives me the square root of 3 over 2? Pi over 6. And then let's move around the circle. What's the one in the second quadrant? 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those are the solutions that occur in one revolution or on one period.
So
right?
we're just basically, if it's saying something like, cosine X, blah, 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 we just like go around the circle and find out like, where that cosine is and see what the angle is in radius.
Exactly.
That makes more
That's
sense.
the end, that's the point of it. So now we've done the square root property. Okay, we did collecting like terms, factoring, square root property. This is what we've done to solve it. This one's a little bit different. And I will point out as you write that down, the previous problems that we've done have all had, if you look at their equations, they've all had the same trig function. There's only been one function in them, right? So this is the first one where we're introducing an equation where I have two functions in there, right? I've got both a sine and a cosine, tangent. I've got a sine and a tangent in there. Now, this is a tricky one, so I hope that somebody tells me what to do, and I really kind of hope you're wrong. Like, I want you to be wrong. What do you want to do?
Change tangent to sine or cosine.
Let's not use an identity yet, okay?
Oh,
I
so
don't know
what
if you can
we,
do it, I probably think you can, but we're not gonna do that in this.
so could we just move the sine X over and make it negative?
Man, that's exactly what you're supposed to do. How many of y'all wanted to divide? Did anybody want to divide by sign? Divide both sides by sign? Come on.
No, but that makes sense. I think that would actually.
Okay, well, because I usually have about half the class who wants to do that. Y'all have met some people in here, right? So if I divided both sides by sign, okay, I'm just gonna do it to show you why it's wrong. All right, so let's say that you're at home and you don't remember what you're supposed to do, and you say, okay, well, I've got a sign on both sides, I'm gonna divide by a sine X.
So you had tangent over sine X.
Well, those are gonna cancel. So I would be left with tan X is equal to what?
1.
All right, so what angle, when I take the tangent of it, do I get 1? Pi over 4 and where? So it's positive, so I'm gonna have two angles. Tangent is positive in 1 and 3, so it would be 5 pi over 4. All right, so that's maybe what you would initially think. Let's go with your correct solution here. And instead, sine X, tan X minus sine X is equal to 0. I'm going to subtract sine X and I'm going to gather all of my like terms up on the same side. Now you notice like what I can do here? I can factor. So I would have sine X times tan X minus 1 is equal to 0.
Why did you minus 1?
When I divide both of those terms by sign, I still get a 1, right? So you have to remember that when you factor out from this term here, I have to leave a 1 to hold its place, right? I'm
Oh.
dividing.
Okay.
So if I distribute back in, I better get what I started with,
Oh, okay.
okay?
That makes sense.
So now I have these factors that are set equal to 0. I would set each equation equal to 0. We already know what happens for tan X equal to 1. That gives me pi over 4 and 5 pi over 4, because we said that already. What happens when what angle, when I take the sine of it, do I get 0? It would be
0 over 2 would be.
It would be 0.
And then pi.
It would be 0 in pi, because it's a quadrantal angle. So how many solutions do I have with the correct way to solve this? 4. How many solutions do I have with the incorrect way?
2.
So I accidentally lost 2 of the solutions by dividing. All right, so you don't want to do that. Don't do that. Apparently, we're going to do that anyway, so that's good. Okay. Questions on this?
Do you want to keep both of your trig functions or all the trig functions in the equation so that you can solve for each of them?
You'll see that we're going to use an identity in another problem. But I didn't have to use an identity in this one because I could just use factoring. I could get them on the same size, set them equal to 0, and then factor.
So why do we pull up sin x by itself, like they're technically together, right? So why would they be split apart?
What do you mean here?
No, the middle section.
Here,
Yeah,
I factored sine out of the two terms.
so you treat them separate?
Other questions? Okay. So that's really kind of the algebra that you're used to. It just looks a little different because we got sign words in there, but in essence, the process is the same, right? For it. This is a little bit different where I want to solve equations that have multiple angles or half angles, so to speak. And again, I'm restricting this to only looking at the solutions that are occurring on the interval between 0 and 2 pi, right? So when you understand that these values here, right, that are in that argument position, those are the angles, okay? And that number 2 is telling me that I'm going to multiply the angle twice, right? Or another way to think of it is I'm going to go around the circle twice, right? If I'm thinking of going around a circle, all right? So so that makes a difference when we're looking at this because this is what I would call a double angle equation, so to speak, then we have to adjust what we're looking at. So it's because of this 2x that we're going to make this adjustment. What we have here is if I've restricted my domain, right, my x values to be on the interval between 0 and 2 pi. So that's a lot of symbols there. It says x is contained in the set, let's say, on the interval between 2 pi. All right. So if that's what we're restricting our domain to be, but the angle that I'm looking at right here is 2x, then I am now going to look for all possible angles between 2 times 0, which would be 0, and 2 times 2 pi, which would be 4 pi. In essence, I'm going to go around the circle twice, right? So I'm no longer looking for angles between 0 and 2 pi. I'm looking for angles between 0 and 4 pi. So when I come over here and now I address this equation, right? This says the tangent of some angle, forget whatever that 2x is, forget whatever that is. It's just saying the tangent of some angle, there's a bunch of them, the tangent of some angle is equal to the square root of 3. So what angle, when I take the tangent of it, do I get a positive square root of 3?
Pi over 3.
Pi over 3, okay? So I'm up here at pi over 3. So I'm going to write this down. 2x would be equal to pi over 3. Where else am I at for a positive tangent? If I'm in the first quadrant, I also have to have an angle in the third quadrant. Third quadrant, so I would be down here. And what would that be? 4 pi over 3. Right? 2 pi over 3, pi over 3 for the first quadrant, 4 pi over 3 for the second quadrant. Are we good with one time around? Those are the angles that happen when I go around once. So if I go around again and I hit pi over 3, what value would that be?
7 pi over 3.
So I have another angle at 7 pi over 3. Keep going around and I hit 10 pi over 3. That's right. Those are the 4 angles that I would hit if I went around 0 to 4 pi. Okay, so if I usually draw a picture and I keep rotating around. so that I can figure out those coterminal angles. Now, I haven't solved for x. So now I've got to come in here and I'm going to divide everything in here by 2, which is the same thing as multiplying by 1/2. So that would be pi over 6, 4 pi over 6, 7 pi over 6, and 10 pi over 6, which of course you would reduce those if you needed to, which we do. Okay?
But
And if you are ever questioning it, how can you check your work?
Plug in X.
Plug in x to the original equation, right? Because if I plug in x to the original equation, notice that as soon as I plug it in right there at that argument, I now multiply it by 2, don't I? Okay, so it's a little odd when you look at these the first couple of times, but that's what we're doing. So that's us restricting it there. And okay, now let's look at this next one. Rather than us, well, let's talk about the domain. That would probably be the easiest. So again, I have restricted the domain so that I'm only looking at angles between 0 and 2 pi. But notice that the argument for my function is dividing x by 3. So I'm going to change and I'm going to adjust my domain to now divide everything by 3. So 0 divided by 3 is just 0. 2 pi divided by 3 is 2 pi over 3. So what this says is I'm only looking for angles on the interval between 0 and 2 pi over 3. Okay?
so how exactly, so are you just basically dividing it over x or?
I'm taking x and whatever x is, I'm either, in this case, I divided it, right? So I'm adjusting the domain. Originally, we were looking for values between 0 and 2 pi, but here I'm saying, okay, well, my x values are going to be divided by 3, so I only want to look for those values then that are divided by 3 on that interval, okay?
That part makes sense.
Okay, so when I take the sine of some angle, I get positive 1/2, right? When I take the sine of some angle, I get positive 1/2. So we're talking first and second quadrants, correct? So the sine of what angle? When I take this, whatever, pi over 6. Okay, so I'm at pi over 6. And what would my second quadrant angle be?
Wouldn't that be 4 pi over 6?
How about 5 pi over 6? Okay, so in the second quadrant, we all agree that when I take the sine of 5 pi over 6, I get 1/2, right? What did I restrict my domain to be though?
2 pi over 3.
2 pi over 3, which is here. 5 pi over 6 falls outside of
Our domain.
our domain, so I ignore it in the way that I have restricted this, right? So I only have one angle that I'm technically dealing with here, right? So I'm not done because my angle is divided by 3. So if I divide by 3, that's the same thing as multiplying by 3 over 1, correct? So x would be 3 pi over 6, or in other words, pi over 2.
That's our only solution for that one?
Because we restricted the domain.
Well, what are we gonna do with the 1/2 though?
That's the solution. Plug it back into the equation and see if you get 1/2 on the right-hand side. Okay? All right, do we understand how that works? Do you understand what I did? Why did I adjust my domain? Based on the angle, why did I adjust my domain?
If the period is being changed.
Because I've restricted the period, right? I have said for whatever reason, I only want to look at the measure, I only want to look at the angles on this one period, correct? So we had to adjust our period accordingly, the X values accordingly, the input. What if, however, I said, okay, I want to know all the solutions. We have to rethink this. For all solutions,
Is this this problem?
I just want to come back and revisit it and talk about it in another way. If I wanted to know what all the solutions were, then we said the sine of pi over 6 gives me 1/2. And we said the sine of 5 pi over 6 gives me 1/2, correct? Okay, so all solutions. So we've gone back and we're addressing this differently. If I have all solutions, then I'm not restricting the domain anymore, right? So how do I go find the next angle that is coterminal to pi over 6? What would I do? I would add 2 pi n. And keep going. You're right. It's like 2 pi plus or 2 pi n for all of them. And the same thing for 5 pi over 6, right?
What's the n represent?
The number of times I've gone around the circle.
Oh, okay.
So 2 pi n, right? These are all the solutions that give me 1/2 or x over 3, right? But I'm not done because I'm dividing x by 3 here, correct? So now I will multiply everything in here by 3, which means x is going to be 3 pi over 6 plus 3 times 2 pi n. There, did you see how I did that? It's kind of tricky. Or 15 pi over 6 plus 3 times 2 pi n. In other words, when I simplify this, pi over 2 plus 6 pi n and 5 pi over 2 plus 6 pi n. This is for all solutions. Okay? So they get a little trickier when we have this angle that is more than one, let's say, right? It's not just a single angle. You're either doing it by a third or you're doubling it or something like that. You also have to adjust your process. So this is what happens if I wanted all the solutions. We came up with the values for 0 to 2 pi, and then we added the 2 pi in to indicate coterminal angles, and then we adjust it by whatever we're doing to the angle. We adjust the iteration by whatever we're doing to the angle. Does that make sense? So there's two different thoughts here. This one is me adjusting it because I restricted the domain. So I also have to restrict the solution for this, the angles. This one in green was all solutions. Okay, so just so long as you can see the differences between the two. Those are multiple angles. Or fractional angles, I should say. Now let's look at this one. In this one, we can see that we have two separate trig terms. Right, I got a sine and I have a cosine. I can't exactly rearrange it, right, like I could before where I gathered all my terms up and tried to factor a GCF out. That was our strategy before. So instead, we're going to look at this and we're going to say, okay, can I rewrite this so that it's all written in the same term, right? And I can. So in looking at sine squared, can I rewrite sine squared in terms of cosine? Can I replace sine squared with an equivalent cosine something?
Yes.
All right, using the Pythagorean identity. So this becomes 2 times 1 minus cosine squared x plus everything I still had. Now, I'm gonna simplify it, but now you can see that everything in there is in terms of cosine. Okay, so we distribute my 2. I get 2 minus 2 cosine squared x plus 3 cosine x minus 3 is equal to 0. I'm gonna write this as -2 cosine squared x,
Where'd you get the -2 from?
-2 right above it,
Oh,
plus 3 cosine x minus 1 when I combine the 2 at the front with the -3 before the equal sign, right? I'm collecting like terms right there. Where does that mean? Right here. I just brought it down, right? This is right here. Oh, is that right there? Oh, okay. And then this 2 combines with that 3, that -3. So I'm collecting my like terms, but I'm writing it in descending order because that's how we factor. What's the other thing that's important when you factor? What do you want that leading coefficient to be? Positive, always positive. So I'm going to multiply every term in here. That's what I'm doing mathematically. I'll multiply every term in there by a -1. So I'm going to change every term in here. Multiply both sides by a -1 and it changes the sign of every term in there. Now my leading coefficient is positive and it's much easier to factor.
So do you have to make the 0 negative?
Well, it doesn't have any effect on the 0 because 0 times anything is still going to be 0. It's neither positive nor negative. So that would,
But if it was like not 0, then you would have to.
yeah, it would have to change it. So if I factor this, I've got 2 cosine x minus 1 cosine x minus 1 is equal to 0 because I get -2 plus a -1 gives me back the -3 I started with. Now we go back and we've got our 2 separate equations. So I go 2 cosine x minus 1 equals 0. Cosine x, or 2 cosine x is equal to 1. Or cosine x is equal to +1/2. Cosine is positive in which 2 quadrants? 1 and 4. That's right. So what angle, when I take the cosine of it, do I get 1/2? In the first quadrant, that's going to be what?
Pi over 3.
Pi over 3. And in the fourth quadrant, what is that going to be? 5 pi over 3. Okay. Now coming back up here, cosine x is now equal to 1. That's a quadrantal angle. That's right. That occurs when x is equal to 0. So there are 3 solutions to that one. Do you see how important your unit circle is to know? Right? This is how come we have to know it, so that we can solve these equations in this part and simplify our identities in the next 2 or 3 chapters. So everything, all that memorization, and keep working on it if you don't have it down, because it's going to really pay off if you can get it down. Are there questions on how I got these answers? So coming back up here to review what strategy we were looking at, we had 3 terms. One of them was quadratic. So we're thinking, okay, could I somehow factor this thing? And I can't right now the way it was because they're not the same terms. Okay, they all have to be the same trig word, for lack of a better description. And we used an identity to be able to get that. Turn them all into cosines and we were able to move on. Let's look at this one then. cosine x minus sine x is equal to -1. Again, I don't have the same trig functions up there. There's no way for me to gather like terms and try to use a factoring property in this case. I can't necessarily use a Pythagorean identity. So let me show you a trick that you can do. And it is kind of like a trick, all right? We know sine, cosine, and 1 are all related by the Pythagorean identity, correct?
So couldn't you just move the 1 over and then when it become a Pythagorean identity? It
No,
has to be
because-
squared.
It has to be squared, that's right. So if you think about the Pythagorean identities, they're always dealing with their functions being squared, okay? So I can, because of that, because I can see this relationship here, I'm going to square both sides of this equation. So when I square the left, this is our jingle, remember, square the first, double the product, square the last, right? Square the first, double the product, square the last, or do FOIL, I don't care, is equal to 1. So far, so good? Shake your heads, yes or no? Okay. Now, see, remember, we practiced something similar to this at the beginning of the class. What do you notice about those two things right there? That they equal 1, don't they? So this is going to be 2. Sorry, this is going to be 2 cosine x sine x plus 1 is equal to 1. Right? Okay. Now I'm going to subtract 1 to the right-hand side. 2 cosine x sine x is equal to 0 now. Divide off the 2 and I get, yes, sir?
Would the 2 in cosine x sine x not be negative since you're adding?
It would be, yes, thank you. Good catch. Negative, negative, negative. Now let's divide off by that -2. And I get cosine x times sine x is equal to 0. Cosine x times sine x are factors that are equal to 0. So now I'm just going to take cosine equals 0 and sine equals 0. So what angles, when I take the cosine of it, do I get 0?
Pi over 2.
And where? Pi over 2, 3 pi over 2. How about sine
0.
and pi? All right. So using an identity to be able to, well, squaring both sides. Now, the thing about this is whenever you square an equation like we just did, you could potentially introduce false solutions, right? So you actually, I am the queen of not checking very much things, right? So this is the one time when I'm going to tell you, you have to check your answers for this. No other time am I really telling you to go in and check your solutions. You can if you want to check your work. But this is the time, because I've squared the equation, because I've squared both sides, you need to go in and check and see if you have any solutions that are not in fact solutions, okay? And how would I go about doing that? So I'm going to plug each of the solutions in to the original equation and see that the left-hand side equals the right. What's another way I can do it if I want to be just fast and lazy? I would graph it, and you told me this before. How would I graph this? The left-hand side and the right-hand side, correct? So, in the interest of time, here I've done that. Okay, so I let y equals the left-hand side, cosine x minus sine x, y equal the right-hand side, which is equal to 1, and I wanted to find out where the intersection for these functions occurred at. Okay, and you can see that the intersection occurs at 0 and 3 pi over 2. If we are only talking about the interval between 0 and 2 pi, right? Because it's going to keep repeating. So really, if we're only interested in the answers between 0 and 2 pi, then I have two solutions that occurred, 0 and 3 pi over 2. So what we inadvertently did by squaring the equation is we introduced two false solutions, which is why we have to check them. So the actual solutions to this that we are going to keep are going to be 0 and what did I say, 3 pi over 2? And we saw that because we checked them. If you algebraically check them, you'll find out that when I plug in pi over 2 into the original equation up there, I'm not going to get -1. Okay?
You plug it in with, like, with it being squared or?
No, go back to the original. All right, plug it into the original. Okay? Yes, you had a question?
Yeah, on your graph, you had the second equation, y equals 1, but in this one it's -1. Does that change?
Oh, it probably would. It probably would. Good catch. I don't know what I had in there. We can look at the answers, all right? All right, I'll look at that in a minute, but throw it out if it doesn't work, all right? All right, let's quickly move on to this one right here. 3 sine squared x minus sine x minus 2. Equals 0. What is our first method of solving a quadratic equation?
Factoring.
Factoring is first choice, okay? These are both prime numbers. Let's try trial and error. So I would have 3 sine x plus something, sine x minus something, and I've got a 2 in the first and a 1 in the second, which gives me -3 sine x plus 2 sine x is a -1. So that's right. And it was set equal to 0.
But when,
So trial and error tells me that that was quick, right? Okay. Okay, now let's go in and solve this. 3 sine x plus 2 is equal to 0. Subtract 2, I would get 3 sine x is equal to a -2. Divide both sides by 3. Sine x is equal to -2/3. Do I know a value off the unit circle that gave me 2/3?
No.
Then this is a calculator question. That portion is, all right? We'll work on it in a minute. This next one, we would have sine x is equal to 1. That's a quadrantal. Therefore, x has to be pi over 2. Pi over 2. +1, yeah. Okay. Now, just remember that we are solving all of these functions on the interval between what? 0 and 2 pi. Those are all positive angles, correct? Okay. So when we use our calculator, says the inverse sine of -2/3. All right,
Why would we do the inverse sine of 2/3?
on the calculator, because I'm looking for the angle.
Okay.
Inverse is always going to be angles. What value, tell me to, let's have 4 decimal places. What value do you get when you take the inverse sine of -2/3?
0.7297.
Is it positive or negative?
Negative.
Okay, so -0.7297, are you in radians?
Oh,
I hope we
no.
were,
I'm in
right?
radians.
Okay, yeah, we're in radians. Now, I'm gonna back up because I needed to point this out. Sine x, so I'm looking for an angle that when I take the sine of it, I get a negative value. What 2 quadrants would that normally be in?
3 and 4. So, yeah, 3.
Quadrants 3 and quadrants 4. Remember that when we take the inverse function, what does our calculator, where does inverse sine live? What 2 quadrants does that angle live in? 1 and 4, right? 1 and 4, and we restricted it. Remember, we restricted it to only look at negative angles, right? I got 1 positive value and I've got 1 negative angle. So when you took the inverse sine of -2/3, you got this angle of -0.7297, correct? That's what your calculator returned for you. But I want to know, because I'm looking for the angles when I take the sine of it that give me -2/3. Those angles are going to be positive, right? Because I'm looking for angles on the interval between 0 and 2 pi. How do you suppose I am going to get this angle here in the 3rd quadrant? How will I get that angle? What is this angle right here? Starts with an R. It's a reference angle, right? It's a reference angle. How do I find this angle then in the 3rd quadrant using a reference angle?
180
I would add
or
to 2 pi, right? So ignore the negative sign for just a minute and let's consider it as simply a reference angle, right? All right. And I am going to take that reference angle, that small slice of the pie, that acute angle that we're looking at, and I'm going to add it to a pi. So pi plus 0.7297. And what will I do then to get this angle, the positive angle, in quadrant 4?
2 pi minus that.
2 pi minus my reference angle. And so we're already using the calculator with decimal values, so you're going to use the pi symbol from your calculator and tell me what you get.
We're still in radians, right?
Yes, sir?
For the pi plus 0.7297, I got 3.8713.
Okay. And then what about for the 4th quadrant?
5.55349.
5.55.
35.
That's right. So those are the 2 angles that give me negative sign, right? Coming from the 3rd and the 4th quadrant. And then we also had my pi over 2. Those are the 3 solutions on the interval between 0 and 2 pi. What if I wanted to know all the solutions? What can I just do here?
So that
Tack on,
plus 2 pi in, right?
tack on plus 2 pi in for all the solutions, right? Because that's co-terminal now with what I'm looking at. Check it using your calculator. You'll find the intersections to be those decimal values.
Wait, can I do that?
two came from up there. I just wrote them all in the same spot. So now when we have to use our calculator, it's a little bit more involved, especially if we are looking at the interval, if we've restricted the interval, okay? I'm looking at the interval that are all positive angles and you have a negative angle, you have to adjust that, okay? So the last one we're gonna use is the quadratic formula. And hopefully you all remember the quadratic formula, but it's negative b plus or minus b squared minus 4ac all over 2a. And those a's, b's, and c's come from what?
Angles. No, wouldn't they all come from that equation, the quadratic equation?
They come from the coefficients of our quadratic equation,
Three
don't
would
they?
be A, one would be B, and the negative one would be C.
Okay, so we have A, we have B, and we have C, right? They come from our quadratic equation. So it works pretty much the same way. Using our quadratic equation, and this does not factor here, all right? You can use trial and error, but I'm going to tell you right now, it doesn't factor. So our function sine theta is equal to our quadratic equation. That's how we interpret this. So I would have negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's what you're going to put in your calculator. I need to know, because this is obviously a calculator question now. So I want to know what two values, I just want to know what this is when I simplify it. Remember, I have 1 plus this divided by 6, and I have 1 minus this divided by 6, right? I can simplify that further if we need. I've got 1 plus the square root of 13 over 6 and 1 minus the square root of 13 over 6 when I simplify that. So to 4 decimal places, tell me what values you get.
The positive 0.7676.
Positive 0.7676, and what do we get?
0.4343 for the negative.
Negative 0.4343. So this says that the sine of theta is some positive value, and that the sine of theta is some negative value. When I take the sine of an angle and I get positive values, what two quadrants do I end up in? Quadrants 1 and quadrants 2. When I take the sine and I get a negative value, what two quadrants am I in? Quadrants 3 and quadrants 4. So now we have to come up with the angle measurements that are equivalent, right? What angle, when I take the sine of it, gives me 0.7676? That occurs in 2 places, doesn't it? So we're going to take, all right, like this. So we're going to take theta is equal to the inverse sine of 0.7676. And your calculator returns for you what?
0.875.
What, Isaiah?
0.875.
0.8875. 1, is it 1?
Yeah.
Okay, so this reference angle here is 0.8751. That's the first quadrant. How about the second quadrant? How am I going to get that angle?
pi minus that.
pi minus 0.8751. Remember reference angles? Okay. And over here, we would have theta is equal to the inverse sine of negative 0.4343. What's that value?
Negative 0.4492.
Okay, so that is this angle, isn't it? That is a negative angle, yet I want the positive angle from the third quadrant. So I would take pi plus 0.4492 and 2 pi minus 0.4492.
Why are those the quadrants 3 and 4 on the second one? One is on the first one.
Why do I have angles that are occurring here in quadrants 1 and 2? Is that what you're asking me? No?
I mean, like, 0.7676 is just quadrant 1 and 2. Above that in blue. Why is it just 1 and 2?
Okay, so the sine of some angle
Oh,
gives me a positive value. Oh no, it gets a little confusing with all the decimals in there. So the sine of some angle gives me a positive number, which is that one. The sine of some angle gives me a negative number. That's how I know what quadrant they're following. Okay, so we should have, what, 0.8751. What's the next one? 2.2665? Is that right? Yeah? Y'all don't know? Okay. How about the next, how about quadrant, this one over here? Is it 3.5 something? Okay, and then what do I do if I want to know all the solutions? Add 2 pi n. Now, why am I adding 2 pi n?
Because when the end, you get to pi two in the number of times you go around.
So 1 period, right? 1 period for sine is 2 pi n. What's the period for cosine? 2 pi n. What's the period for tangent? Pi. So if you're doing tangent, you would add pi over n. Okay, because it would be, it's based on 1 period.
Pi over n.
Pi n. Pi n. All right. Calculator ones get a little more complicated because you've got to start adjusting these values. Okay. But all in all, the solving of these is almost the same as what you've been doing. Okay. We have to make sure that we pay attention to if they are all in the same function, right? Trig function, if they're all the same trig terms. All right, questions on that? No? All right, so what I want you to do, just work with your people at your table. And there are 8 problems that you have there. You can come up and check your answer with me. I'll be coming around to help you out as well. But you're going to try to get as many of these problems done before we have to leave. All right, I would encourage you to, even if you work by yourself, to at least ask your neighbor to check and that kind of stuff. Try to do all 8, yeah.